Okay, this is going to be the video for section 1.2 of differential equations, initial value problems. So this time I'm going to try a little different display technique to try to make my pen work a little bit better here. All right, so often when we have a differential equation, then the solution will actually be an entire family of functions that are separated by just a constant. Um, and that means that any function in that family would therefore work as a solution to the differential equation. So for example, let's say we were given this differential equation, y prime plus 2xy squared equals 0. And through techniques that we'll learn later in the course, we could figure out that any form that has the function, any function that has the form y equals 1 over x squared plus a constant c, where c is a numerical constant, anything of that form is a solution to this differential equation, okay? Regardless of what value you choose for c. Such a solution is referred to as a family of solutions, or sometimes we call it the general solution, which is typically what I would call it. All right, and if you were to graph all this family of solutions, you would get a variety of what we call solution curves. So if you set c equal to 0, then you would get this green curve here, right? Has two pieces to it because it has an asymptote here at the x-axis because it's undefined when x is 0. If you set c equal to -1, then it looks like a curve like this, and something like this in the middle. If you set c equal to -2, it'd look like this. So you have a different curve depending on what you set the c at. But all of those curves are solutions to this particular differential equation, right? The equations describing these curves, all, if you take the derivative of them and plug that in plus the original equation here, it makes this equation true. All right, so often the differential equation represents some real world situation where, in addition to the differential equation itself, which is giving us information about how the rates of change of the variables relate to each other, you may also know something about the state of the system under a particular circumstance. So for example, frequently one of the variables is time. So this might be, for example, knowing the position of something or of everything at a given time, right? So this extra knowledge serves as a constraint to the problem, and it's known either as a boundary condition or an initial condition, okay, or boundary value. Sometimes different books use different words under different circumstances. Our textbook tends to use the word initial conditions. Okay, so if we know the initial conditions, we can use that to figure out what the particular constant needs to be. So let's say, for example, we have this differential equation, and what this is telling me is that the rate of change of y with respect to x is in some way related to the value of x and y, right? And we know that from being told that there's this particular family of solutions where c is anything will be in an equation. But let's say we know this initial condition. We know that when x is 3/2, this is telling me that y has to be 4/5, okay? So that means that if I were to plot all the different solution curves on the xy plane here, then this initial condition represents a point, right? When x is 3/2, y is 4/5. And if I went out to that particular point, x is 3/2, y is 4/5 here, right? Only one particular solution curve actually goes through that point. And so there is a particular value. In this case, it happens to be that the c has to be set to -1. Okay, now when we fix the constant so that we get a particular solution curve to go through an initial condition point, then the result is called a particular solution. So the family of curves is called the general solution, or the family of solutions. But when we fix the constants in the general solution, we get a particular solution that not only satisfies the differential equation, but also satisfies the initial condition. Okay, so you can think of the initial condition as like the point that you plug in to be able to solve for the constant. That's the way I think of it essentially. Okay. And of course, we can find that particular solution without having to graph. We can do that algebraically. So these are called initial value problems when we're given some way to find the solution, but then we're given an initial condition to establish the constant to find the particular solution. So let's say I have this differential equation, and the one we've been working with, we have this, and we have this initial condition that when x is 3/2, y is 4/5. Rather than graphing, what we could do is just take the general solution, y equals 1 over x squared plus c, and substitute 4/5 in for y and substitute 3/2 in for x, and then solve for c. So that's what we'll do. We'll put 4/5 in for y, and we'll put 3/2 in for x, and then solve this algebraically. So um, let's see, I guess we could yeah, multiply this out. So it's 4/5 times 9/4 plus c equals 1 when we multiply both sides by that. So you'd end up getting, what is that, 30. You know what, actually, let's multiply both sides by 5/4. So you get 9/4. This is the c here. 9/4 plus c equals 5/4. So c is 5/4 minus 9/4, which would be -4/4, which is -1. So that's how we would typically actually solve for the c. We would not graph it and then see which one literally goes through the initial condition point, but we would use the initial condition as an xy pair to plug in and then find the constant. Okay. All right, if you have higher order differential equations with second or third derivatives, then typically there's more than one constant, one for every uh, number in the order. So let's say, for example, we had this differential equation, y double prime minus y equals 0. And we'll find out later in the course that the solution to this style of an equation is a family of solutions of the form y equals one constant e to the x plus a different constant e to the negative x. So if we knew that, but we also knew the initial conditions that the y when x is 1 is 0, and the derivative of y when x is 1 is e, that would give me enough information to be able to fix the two constants to get the predictor solution. Right, so what we would have to do here is let's go ahead and start working with this, right? We've got this right here. So I could go ahead and plug this in, right? When x is 1, y equals 0. So if I take the solution and plug in 0 for the y, c1 e to the 1 plus c2 e to the negative 1, okay? So that's an equation, but it has two unknowns, right? So I'm unable to solve for the constants because there's two equations or two unknowns in only one equation. But I also have this equation. So to use this equation, I have to take the derivative of the solution. So y prime would be, that's interpreted as dy dx. So you can think of that as dy dx because the independent variable here is x. So this would be the constant. The derivative of e to the x is the copy, e to the x. And then we would have, let's see, the constant here. The derivative of e to the x is the copy, but times the derivative of the inside, which is -1. So this is going to be c1 e to the x minus c2 e to the negative x. Okay, so if I use this, this is telling me when x is 1, y prime is equal to e. So if I plug that in, let me do that over here. I would have, this is y prime. So y prime, let me just do it right here actually. Y prime is e whenever x is 1. So e to the 1 minus c2 e to the negative 1. And that gives me a second equation. So if I were to write this out, it would be like saying, in fact, let me write it a little bit different. I'll change the color here. This equation can be written as e to the 1 c1 plus e to the negative 1 c2 equals 0. Right? And this one, this equation here, can be written e to the 1 c1 minus e to the negative 1 c2 equals e. Okay, so that forms a system, and I could use any technique I want to solve, but actually I notice that these are already set up that if I just add them, this term is eliminated. So I end up with e c1 plus ec1, which is 2e c1 equals 0 plus e, which is e. And when you divide, let's see, both sides by e, you would get 2c1 equals 1, and therefore c1 has to be 1/2. And then I could back substitute. Let's take this version of the equation here, and I would have e to the 1, and now I know c1 is 1/2, plus e to the negative 1 c2 equals 0. and I could solve this for C2 now. So if I brought this to the other side, I would have, let me write this a little bit differently. Let me give a little more room here. So I would have e to the negative 1, which is 1 over e C2. And if I bring this to the side, it's going to be negative 1 half e, right? So if I now multiply both sides by e, I'm going to get that C2 is negative 1 half e squared. And what that means is my particular solution is now I can take my general solution, y equals c1 e to the x plus c2 e to the negative x, and I can fill in c1 and c2. So the particular solution would be y equals 1 half e to the x, and then let's see, we've got plus and then this constant, so minus 1 half e squared e to the negative x. So this is the particular solution. Okay, so what that's saying is not only does this equation satisfy the differential equation that requires that the rates of change relate in some way, but it also goes through the point that makes these two conditions true at the snapshot in time or whatever this represents. Okay, so that's how we find a particular solution. Okay, and then there's one last little thing here to talk about. It's kind of an esoteric thing, but it is in the book and was in the notes last year, so we'll talk about it. Where do we have a solution? Is it true that there's a solution for every point in the domain for a differential equation? And the answer is not necessarily. And sometimes there are multiple solutions, and sometimes there's only a unique solution at different points. So beginning in chapter 2, we're going to start learning techniques for finding the solutions. Here, we're just assuming we have a solution. And if we have further initial conditions, then we can determine the constants to give a particular solution. But another important thing to consider is, will a solution even exist, right? Okay, if so, and we find that solution, is that the only solution or what we call a unique solution? Or could there be other solutions that would also satisfy the differential equation besides the family of solutions that we're finding? So in this introductory course, we'll occasionally trot out some theorems here that you would encounter in more advanced courses, but not frequently. So if you go on to be a math major, this is a much bigger part of what you study. But if you go on to more applied mathematics like engineering and physics, then we're more interested in the results rather than like the subtleties of, okay, it exists except for certain places in the domain. But there is a more formal theorem that says this. It's in the textbook. It says, let R be a rectangular region in the xy plane defined by a between in an interval from a to x between in an interval between a and b, and y in an interval between c and d, that contains in a point x0, y0 in the interior. If f, which is a function of xy, and the partial derivative of f with respect to the y variable are continuous on this rectangle, then there exists some interval which is plus or minus h from the x0 position in the interval AB, and a unique function y as a function of x defined on that interval that is the solution of the initial value problem. Okay, what this is really saying is that if you have a first order differential equation that can be solved for its derivative on the left hand side, that will be equal to a function that we call f of xy on the right hand side. Okay, and then if you take the partial derivative of that with respect to the dependent variable y, then you just look at that right-hand side function and its partial derivative with respect to y. And any place where those functions both exist, in that region of the domain, there will be a single unique solution. Okay, much easier to see with an example. So in the notes, I'm just going to walk through the example that's in the notes for you. Here's the differential equation, 1 plus y cubed and then quantity times y prime equals x squared. Determine where in the xy plane this differential equation is guaranteed to have unique solutions. So first, we take this equation and we reformat it so that it's solved for its first derivative. This theorem only works for first order derivatives that can be solved for a y prime. Okay, so just dividing both sides by 1 plus y cubed, we get y prime is x squared over 1 plus y cubed. Okay, this function on the right hand side is termed f of xy. Okay, and so what we're required to do is to find this partial derivative df dy for this particular theorem, because this is in the form of a quotient here, we're going to use the quotient rule. So it's low d high, but this derivative is with respect to y, minus high d low over low squared. And if you carefully go through this, you end up with this expression here, okay? And then what we do is we look at the function and that expression, and we try to determine if there's any xy places in the domain where those functions are undefined, because those would be places where there is not guaranteed to have a unique solution. So if I look at the original function, x squared over 1 plus y cubed, there's only one spot where we have a problem, and that's where the denominator could go to 0. That would happen if y cubed was -1, and that only happens when y is -1. Okay, so that's one kind of iffy area where we're not guaranteed a unique solution. Okay, and then if we look at the df dy, um, we have the same structure except cube or except squared. So that would again go to 0 whenever we have y equaling -1. So it turns out that that's the only spot, like of the xy plane. You're going to have a unique solution everywhere except any place where y is -1. So there's this one place here where we're not going to have a guaranteed unique solution. But for any other point in xy domain, this differential equation is guaranteed to have a unique solution. All right, it doesn't specify actually what happens at y equals -1. It could be that there are solutions there, but multiple solutions, or it could be that there's no solution. But for every other place except where y is -1, we're guaranteed to have a unique family of solutions, okay, or a unique solution for those particular points. All right, that's it for 1-2. So at this point, you should have enough to be able to do the 1-2 homework.